Welcome to the fourth presentation in Unit 3 entitled The Heat is On. It says it doesn't make a difference what temperature a room is, it's always room temperature. So the learning goals for this particular presentation are that you be able to differentiate between heat and temperature, and you be able to use the equation below to solve for an unknown variable, most specifically heat. So here's what we already know. We already know that energy is measured in joules, that's the standard unit. We know that heat is a type of energy, okay, sometimes it's called thermal energy, and we know that energy is always conserved. Okay, Leibniz, this guy right here, who was also famous for inventing calculus, was the first to actually propose that energy is always conserved in a system. So here's what we learned in the lab. We learned that adding ice can actually decrease or change the phase. Now, if you were to look at this graph is actually showing an increase in temperature as you add heat to a system. You should have found something that's directly the opposite, that as you add ice to a system, the temperature goes down. We also know that water has a specific heat capacity of 4.184 joules per gram Kelvin, and we also know that increasing the mass can decrease a change in temperature. So if you increase the mass, it is much harder to change the temperature of the system. So thermal energy represents the sum of the potential and the kinetic energy. Increasing the thermal energy does not always increase the temperature. So for example, if you have a very small glass and a very large glass of water, this larger glass has more kinetic and potential energy, even though it may not have the same temperature as this one. Temperature is not always the same. Temperature is a measure of the average kinetic energy. So remember, kinetic energy is the energy of movement. So another way of thinking of temperature is how fast the molecules are moving around a room. Are they moving quickly or are they moving slowly? Higher temperature means that they have faster molecular motion. Now, the two conversions, we have several scales for temperature, and the one you're most familiar with is the idea of Fahrenheit. The United States is one of three countries in the world that uses the Fahrenheit scale. It is what you are most familiar with, but the most of the rest of the world operates on the Celsius scale. So the conversion factor between Fahrenheit and Celsius is you subtract 32 and then multiply it by this number right here. That's actually 5 ninths, rounded to put in decimal form. Then, although most of the countries in the world use Celsius, scientists use the Kelvin scale. And the Kelvin scale is just the Celsius scale plus 273. So you need to be able to convert between temperatures. Now, the lowest possible temperature is absolute zero, and it is a theoretical temperature in the sense that we have never reached absolute zero. Okay, now the reason why we have an absolute zero, the reason why we use the Kelvin scale, is the Kelvin scale says 0 degrees Kelvin is my absolute minimum. In other words, I can't have negative 1 Kelvin. Because of that, the Kelvin scale is considered to be an absolute scale. Okay, there is zero molecular motion at this point, and it is the theoretical temperature at which a gas has zero volume. So that's where it comes about. They said, okay, if I cool a gas and it gets smaller and smaller and smaller and smaller, eventually I'll get to the point where there will be zero volume, and that always came out to be the same temperature. It always came out to be minus 273.15 Celsius. So because it's Celsius, they created the absolute scale of Kelvin based on that. So you do need to be familiar with the phases of matter. Matter, not matter. Okay, solids are molecules that are stuck together and allow a small vibration. So solid particles do move, but they move back and forth very quickly and in the same place relative to everything else. So this molecule right here that we've drawn a square around will not move over here. Okay, liquids have freedom of movement, so they can move from here to here and here to here and so on. They can move relative to one another, but they cannot escape gravity. Gas molecules are free to move with a sufficient energy that they can escape gravity. Gas will fill an entire container regardless of the shape of the container, while liquids just fill the bottom. And solids have no freedom of movement and therefore will just stay in their defined shape. Heat, we've defined as the transfer of energy between two objects of different temperatures. So remember, sometimes this is called thermal energy. So heat always flows from high to low. So you'll never sit here at 100 degrees and have a box next to it that's 0 and have this one get higher, go to 110, and this one go to minus 10. That will never happen. Instead, heat always flows from the high temperature to the low temperature. Now, heat can be used to change the kinetic energy, which is related to the temperature, or it can be used to change the potential energy, which is related to the phase. So whenever you add heat or you add energy to a system, that energy has to go somewhere. It either goes to the temperature or the phase. Now the SI unit is the joule because all energy is measured in joules. So now we look at the idea of thermal equilibrium. Equilibrium just means that, equal. It says the systems will always move towards equilibrium. So if you start off with the idea of 0 and 100 and you touch those objects together, they will go to thermal equilibrium when they reach the same temperature. Now, just because you've reached thermal equilibrium does not mean there's a stop of the transfer of heat. Instead, heat is still transferred, it is just transferred much more slowly. Equilibrium means the idea that although energy is transferred, there is no net movement of energy. As a result, however much energy is transferred this way, you have the same amount transferred in the opposite direction. So the first question we have, it says a can of hot soup is placed on a windowsill. Describe the transfer of energy at the macroscopic level. Macro means on a large scale. So because of that, we have something that is very hot. And because it's hot, we can assume that the air around it is cold. Because of that, we say that heat is transferred from the hot to the cold, or another way of saying that is heat leaves the soup and goes to the air around it. The next question says, which has more thermal energy, a single cup of coffee at 80 degrees Celsius or a swimming pool at 10 degrees Celsius? Now, when you think of thermal energy, remember thermal energy is the sum of the kinetic energy and the potential energy. So if you were to look at this, even though this right here has more energy per volume, because the volume is really small, the sheer volume of this means that this is going to have way more energy than a single cup of coffee. It says which travels faster at the same temperature, O2 or N2. It says justify your answer using the clear method. So remember, temperature is very similar to kinetic energy. This right here means proportional. So because of that, if you have an increase in temperature, you have an increase in kinetic energy. So because of that, we can say that since they're the same temperature, they have the same kinetic energy. Now we have to go back to our definition of kinetic energy. Remember, kinetic energy, we said, depends on mass and it depends on velocity squared. So because of that, we want to know which one travels the fastest. And so the one that travels the fastest, we look at the equation, 1/2 mv squared. The one that travels the fastest is going to be the one with the lowest amount of mass, because remember, this right here is a constant. It's the same number. So because of that, we would pick the one that is the smallest. So we would look at our periodic table. We say, okay, which one of these has the least amount of mass? And that would be nitrogen. Finally, it says a single tub of popcorn at the movie theaters can have 3,200 calories, and it says kilocalories. Remember that from earlier in this unit. How many joules is this? You would say 3,200. And then you would say capital C calories. Remember, that's a dietary calorie. And then we would say in one capital C calorie, that is 4,184 joules. So once we multiply that out, you end up getting the number of joules in a single tub of popcorn, which ends up being a really large number of about 13,400,000 joules, which is a lot of energy. It says describe the flow of heat on a microscopic level if a 300 degree Fahrenheit piece of iron is touched to 400 K brass. So the first thing you need to realize is that these two are not in the same system of measurement. Because of that, we're going to have to convert them so that they're the same. We want to stay in Kelvin because that's what we use in science. So because of that, I need to convert 300 degrees Fahrenheit. So remember, the equation that I have to convert to Celsius is 5/9 of F minus 32. So this is my temperature in Fahrenheit, so I plug it in there, and I would get the temperature in Celsius is equal to 5/9 of 300 minus 32. So I get my calculator out, and I say 300 minus 32, multiply it by 5 and divide by 9, and I get something like 149 degrees Celsius. Then I need to take this and I need to convert it into Kelvin by adding 273 to it. When I do that, I end up getting roughly 422 Kelvin. So if you're trying to describe the flow of heat on the microscopic level, what you would say is that the molecules in the iron are moving very, very fast. So you have fast iron. So those are moving really, really, really fast. Then what happens is they come into contact with the brass, which is hot but not nearly as hot. So a molecule from the iron can collide with the molecule from brass. And when they collide together, some of the energy is transferred into the brass. So the brass starts to move faster while the iron starts to move slower. And as a result, energy is transferred. So now we need to look at specific heat capacity. Specific heat capacity is the energy that's required to change 1 kilogram of a substance 1 degree. We tend to use kilograms in the physics portion of this, and if you're looking at it from a chemistry perspective, you tend to see grams. Now, insulators, things that insulate from heat like styrofoam, or even wood is a good conductor, have a very high specific heat capacity. And conductors have low specific heat capacity. So if you see wood takes 2,900 joules to change the temperature 1 degree. Copper requires almost an eighth of that, so it requires much, much less energy to change the temperature of copper. Okay, specific heat capacity trends, generally speaking, as you increase the temperature, or as you go from a solid, solids have high heat capacities, liquids have smaller heat capacities, and gases have really low specific heat capacities. That means that it is easy to change the temperature of gas. It is difficult to change the temperature of solids. Okay, there is an exception, and that exception is water. Just like whenever there's always an exception, it's always water. And that has to do with the bonding of hydrogen. Okay, the liquid stage of water is actually the most specific heat. That is not normal. It is one of the things that is unique to water. Okay, you have an equation right here, and this is called the specific heat equation. It relates mass, specific heat capacity, and the change in temperature to what we call heat. Heat is our energy. So whenever we have our energy, it's going to be measured in joules. M is mass, and it's going to be measured in kilograms. The specific heat capacity is unique to the substance that you're looking at, and it's the amount of energy required to change the temperature 1 Kelvin whenever it's 1 kilogram. And then finally you have the change in temperature. And remember, anytime we see the change in temperature refers to the final temperature minus the initial temperature. So it says, can heat be negative? If so, describe the circumstances that are necessary. So if we were to look at our equation, Q equals Cm delta T, we have to look at every variable. C can never be negative. It has to be positive. The reason why is that's the energy required to raise the temperature 1 degree. So since you're trying to raise the temperature, the heat has to be positive, so that will be a positive value. Mass has to be a positive value as well, because you can't have negative mass. The delta T, though, on the other hand, can be a negative number. Remember, delta is described as the final temperature minus the initial temperature. So if you have the final temperature being something like 0 and the initial temperature being something like 100, that would give you a value of a negative 100. So in other words, the final temperature has to be less than the initial temperature. In other words, the object has to be cooled. If you cool the system down, then you have a negative heat because you're taking heat out of the system. It says, what substances will undergo the greatest temperature change, assuming equal mass? So we have the idea that Q equals Cm delta T. They have the same amount of heat, so that's constant. They have the same amount of mass, so that's constant. So we have some sort of number is equal to C delta T. Since this is a constant number, if you increase this, this goes down. So whenever something has a high specific heat capacity, it will not change temperatures very much. So if it has a low specific heat capacity, it will change temperatures very easily. So in this case, I look and I say plutonium is the lowest one. Because plutonium is the lowest one, it will have the greatest change in temperature. And finally, it says determine the heat required to raise 2 kilograms of water 5 degrees Kelvin. So I would say I want to figure out what Q is. C is 4184. Okay, that's joules per kilogram. I have the change in temperature is 5 degrees Kelvin, or 5 Kelvin. They don't actually say degrees Kelvin. The mass is 2 kilograms. And as a result, you can say Q equals Cm delta T. Whenever you plug in, you would get 4184 times 5 times 2. 5 times 2 is 10, so you end up getting 41840, or 41,840 joules of energy are required to do this.